having defined what we mean by a self-adjoint operator, let's see how Green's formula assures us that the operator appearing in Sturm Liouville differential equations gives us, or is a self-adjoint operator. Alright, now the first example comes from a regular Sturm Liouville problems, where we look at the boundary conditions, which are of the form that u dash of A is alpha u of A for some constant alpha, and u dash of B is beta u of B for some constant beta. And these boundary conditions will complete the definition of the operator L in this class of problems. Now Green's formula tells us we just have to look at this and see if it's zero. And if it is zero, then the operator is self-adjoint. So let's do that. So P u v dashed minus v u dashed from A to B is equal to 0. Well, let's prove it's 0. Is here what? Well, this is P of B expanding it out into u of B, v dash of B minus v of B, u dash of A. Then minus this evaluated at A, so minus P of A, u of A, v dash of A, minus v of A, u dash of A. Trunk, and that A there should be a B. Now let's use the boundary condition and see what happens. Now we know the boundary condition says u dash of A is alpha u of A, so let's use that there. And u dash of B is beta u of B, so let's use that there. But crucially, these boundary conditions apply to every function that L is applied to. So V must also satisfy these boundary conditions, because in order to derive Green's formula, we say L of V. So V has to satisfy the boundary conditions associated with L. Here, these. So that means V dash of A is alpha V of A. We use that there. And V dash of B is beta U of B, V of B. And we use that there. So this becomes P of B, U of B, beta V of B minus V of B, beta U of B, using the two boundary conditions of B on U and B. And the same for this line, minus P of A, U of A, V dash of A, well, that has to be alpha V of A, minus V of A, U dash of A. U dash of A is alpha U of A. Okay, and then you look in there, and what happens, we see that this term is exactly the same as that term and they cancel, and this term is exactly the same as that term and they cancel, leaving us 0. So in this class of problems, the Sturm Liouville operator with these boundary conditions is self-adjoint. Now, as a second example, let's have a look at the so-called periodic boundary conditions. And these periodic boundary conditions are usually used with functions in the Sturm Liouville differential equation, P, Q and R, which are also periodic. Now what we mean by periodic is their value at the end of the interval B is the same as their value at the start. So things like U of A have to be U of B. Similar for its derivative, U dash of A is U dash of B. And for us, P being periodic, we will also invoke that explicitly as being P of A has to be P of B. The differential operator will be self-adjoint if and only if by P U V dash minus V U dash evaluated between A and B, only if that's 0. So let's have a look at it. It expands out to be exactly the same as what I wrote here. P of B into U of B, V dash of B minus V of B, U dash dash of B minus P of A, U of A, V dash of A minus V of A, U dash of A. Now, as it happens, because U, U dash and P at B are the same as what they are at A, we can say this is P of A into U of A, V dash of B minus V and U dash of A. Right, but remember, L is applied to V, so V has to satisfy the same boundary conditions. So V of A has to be V of B, V dash of A has to be V dash of B. So V dash of B is also V dash of A, and V of B is V of A. Right, and then we write out this second line again, minus P of A, U of A, V dash of A, minus V of A, U dash of A. And what you see is everything in that second line is the same as what's in the first, and this second line is negated, so these just cancel completely, and we're left with 0. So the Sturm Liouville differential equation with these periodic boundary conditions, and provided P is periodic, is also self-adjoint. And then as a third example, let's look at Legendre's ODE, which is in this form, 1 minus x squared u dashed, all differentiated, plus lambda u is 0, solved for x between minus 1 and 1. Well, here the differential operator is in Sturm Liouville form with p of x is 1 minus x squared, this coefficient. It's not a regular Sturm Liouville problem, however, but it is self-adjoint because let's have a look at p u v dashed minus v u dashed from A to B. Now, here the interval is A is minus 1 to B is equal to 1. Well, here this is 1 minus x squared, u v dashed minus v u dashed, evaluated at x is equal to 1 minus x is equal to minus 1. And the thing you note is that at x is 1 and minus 1, this 1 minus x squared is 0. And so this whole product evaluated at those 2 points is 0. So that implies here that this linear operator L with this coefficient P is self-adjoint. And the interesting thing here is it's self-adjoint without specifying any boundary conditions on U and V at all. So it seems almost incredible. But it's not that incredible, because one of the things you would have met in solving Legendre's ODE previously is that generally solutions of the Legendre's ODE go to infinity as x goes to plus and minus 1. And it's only very special solutions that don't. And those are the Legendre polynomials. Now what does that mean? It means that generally this term here goes to infinity as x goes to plus or minus 1. So if you take the limit of this product as x goes to plus and minus 1, you won't necessarily get 0. You only get 0 under the conditions that u and v remain bounded as x goes to plus or minus 1. And that boundedness is effective boundary conditions on u and v because it excludes the infinite ones. So L is self-adjoint provided functions u and v are nicely behaved, say bounded as x goes to plus or minus 1.